Okay, so in the last lecture, we studied Biot-Savart law. We studied three different expressions of Biot-Savart law. If we wanted to calculate the value of magnetic field intensity and the thing that we have been given by the numerical or by the examiner was the current, in fact, I, or the line at which that current is flowing, that is dl. And we also studied another example we had in which we have been given the value of J as surface current density. So we modified our equation for Biot-Savart law for surface current density, and then we modified it for volumetric current density. Now we'll try to apply the Biot-Savart law and try to calculate the value of magnetic field intensity H for at a certain point, at a certain observation point, uh, due to the presence or due to the movement of a steady current which is being flown through a straight wire, and that wire is of infinite length. That length is depicted by small l. So we'll talk about it in just a few seconds. The things that we have been given with are the length of the conductor, which is small l, and he's saying that it is aligned along z-axis. And let's draw that thing first. If this is the z-axis, then this is going to be that conductor. So this is that conductor, and the length of this conductor is small l, as mentioned earlier. Okay, another thing that he's saying is that the direction of current that is flowing through this conductor is along z-axis. And what else has been given? And he's saying that this is the observation point at which we have to calculate the value of magnetic field intensity. Apart from that, he's saying that this distance is small r. So we have placed this conductor such a way that half of this conductor is above this origin point and half of this conductor is below this origin point. So we can say that the length above origin point is L by 2, and the length below origin is L by 2. And if, we know that in order to calculate the value of dH, first of all, let's just write the expression for dH was equals to, okay, 1 over 4 pi, in fact I over 4 pi dl cross r hat divided by r square. So if we take a look at this expression, we know that we have to know, yeah, we have to have a segment of this wire as a d as the as dl, so that we can perform our analysis and we can calculate the value of this r square from that dl towards this observation point. So he's saying that let's consider that we have this section and this section. We'll consider that this is, sorry, I don't have space, this is dl, and the direction of dl is in the direction of current, as we have talked about it earlier. So he's saying that if we draw r from this point, this is r, this is from the other point, this is r, and he's saying that the angle that this is making with z-axis, this is theta. This side was called small r, and if this is our hat, oh, what else? Is there anything else? So if we extrapolate this r, this is our hat, and this is the direction of dl. Why are we mentioning these unit vectors? Because we want to know what will be the direction of dh at this point. So we'll curl our fingers toward from dl towards r, and we'll see that our thumb is pointing into the screen, so we'll put a cross here. So if this is the z-axis, we have drawn this thing, and right now we'll try to put the values. We'll say that dl, we take a look at dl. The direction of dl is in the direction of current, which is in the direction of z hat. Apart from that, the length is also aligned along the z-axis, so dl is z hat dz, and dl cross r hat, we have to know the value of this thing. For dl cross r hat, if we take the magnitude of dl out, we'll say that this is dl unit vector cross r unit vector, and the unit vector of dl is z hat cross r hat. And the thing that we have studied earlier, the transformations, will say that z hat cross r is in fact equal to phi hat sine theta. You can correspond to the table that we studied in vector analysis chapter. So dl cross r hat is now equals to dz phi hat and sine theta. This theta is basically this angle between z and r. Okay, so we'll put all of these things. This is not dh because we have mentioned an integral here. This is h. We put all of these values into the above expression. I over 4 pi integral dl across r, it's now can be mentioned as phi hat sine theta dz divided by r square. Okay, and now the limits is, if l by 2 is above, l by 2 is below, this is 0, so this is minus l by 2 and this is plus l by 2. So minus, from minus l by 2 to plus l by 2, this is phi hat I over 4 pi minus l by 2 plus l by 2 sine theta divided by r square dz. There is something wrong with this equation. What's wrong with this equation is that we have theta here, but we have the expression uh, in the direction of phi hat, but we are doing the integration in the form of dz. So this means that we have to transform this z in z's integral into an integral which we can express in the form of an angle, because in spherical coordinate system we do have r, in spherical coordinate system we do have phi, we do have theta, but we don't have z axis. So in order to calculate this thing much efficiently, we need to transform this z into theta or phi, and we need to transform these limits which are mentioned in the form of linear lengths, we have to transform them in the form of uh, theta 2. So for that case, if we want to calculate something, yeah, if we want to do our analysis on this whole conductor and we want to take the limits in the form of theta, then we'll have to redraw this diagram once again. In that diagram we'll have to see that what limits of theta can give us the values for this whole conductor. So if this is the conductor, we'll draw this once again. This was the point. This is R1, this is theta 1, and if we want to analyze this whole conductor, then we'll have to draw another vector from the other extreme end of this conductor, and we'll say that this is r2, and we'll say that the angle that it now makes with z-axis is theta 2. So we have figured out the limits, that if we want to perform our analysis on this complete conductor, then we'll have to integrate it from theta 1 to theta 2. But for this to work, we have to transform this internal dz as well, and we have to transform this r in the form of theta as well, because we have to uh, transform all the things which is inside this integral into their theta's equivalents, if we want to effectively analyze our conductor in the form of theta. So for that case, we know that this was r, this was r, and if we want to mention this r in the form of theta, how can we do this? We can mention this r in the form of theta by using sine component. If we say that sine theta is perpendicular over hypotenuse, and then this is the perpendicular, this is the hypotenuse, or that means small r over hypotenuse, which is capital R. So what is the value of r? Capital R, small r into sine theta, or we can say that the value of capital R is r cosecant theta. So this is how we can mention capital R in the form of small r and cosecant theta. The other thing that we need to do right now is that we have converted this r in the form of theta, and now we want to convert this dz into theta as well. So in order to calculate the value of dz, we'll have to mention z in the form of theta. So in order to mention z in the form of theta, we'll take where is z? This is z, basically this part, this base part of this triangle. So tan is the appropriate trigonometric function. Tan theta is equals to अपना perpendicular over base. But one thing that we'll have to keep in our mind is that this base is below origin, so it is in the negative axis. So this is r perpendicular over base is in negative axis. So right now if we write this z, this will be equals to minus r over tan theta, or we can say it is minus r cot theta. And if we want the value of dz, we'll take the differential on both sides. So the dz, the differential of cot theta is minus cosecant square theta. So minus cosecant square theta, this minus will uh, neutralize that minus sign, so this will become r cosecant square theta. So you need to understand this cosecant square theta and d theta, because we have taken differential, not derivative. Cosecant square theta d theta. So now we have the value of dz, we have the value of r, we have the value of limits. Now we can put all these things back into this equation. So right now I is equals h is equals to I over 4 pi integral, okay, I over 4 pi integral this phi hat sine theta as it is. Instead of dz, we'll write r cosecant square theta d theta divided by, instead of this r square, we'll write small r square, we'll write cosecant square, we'll write theta. This cosecant square will be cancelled by this small r will be cancelled by 1 of this r, and this r is basically constant, so it will come out. Now phi hat is equals to 1 over 4 pi r, and inside we have sine theta and d theta, and the limits are from theta 1 to theta 2. I think we'll have to move towards a new board. So where were we? Phi hat I over 2 pi r integral theta 1 theta 2 sine theta d theta. Now we have a beautiful looking expression for h. Now we can put the value of theta 1 and theta 2 into this equation. So we'll integrate this equation and the equation will come out to be I hat over, sorry, phi hat I into, this is not 2 pi r, it's a mistake, this is 4 pi r, I over 4 pi, and inside this will be cos theta 1 minus cos theta 2. So we have this equation, but still we have to bring out an equation for h for this scenario, which gives us the value of h if we have the value of, if we put in the values that were given to us. And if you take a look at the numerical, at the statement of the numerical, we were not given with theta 1, we were not given the value of theta 2, so we can't put these values into this equation. This means that this equation right here, it is not the final equation. We have to drive an equation in which we can put the values that have been given to us. We can't just perform all this type of analysis and find the value of theta, the corresponding value of theta, and we'll try to put that value of theta into this thing. This is not the way how things work. This means that we have to modify this equation further into, in terms of that things that were given. What things were given to us? Small l was given to us, r can be calculated, or it was given to us because we had the observation point. So we have to convert this thing back into an expression which involves small r that was given, which involves the value of l which was given, which involves the value of I which was given. So we have to transform this thing back to those things, to those terms, so that when we have derived an equation from this thing, it will be easy for us to just put in the values into that expression for any numerical that corresponds or that relates to a current carrying conductor. We just put in the values in that equation, and as a result we'll have the value of h. That is basically the purpose of what we're doing right here. So that means we have to uh, transform this equation further into those kinds of things. So how can we do that? uh, we have to modify, or we have to equate these cos theta 1 and cos theta 2 in the form of those things, in the form of those l by 2s and r by 2s or l's, or those things. So first of all, we'll talk about how to mention cos theta 1 in that form. If we want to mention cos theta 1 in that form, we'll have to refer to the last diagram that we drew, yeah, this one. So if we want, this was r, this was l by 2, this was l by 2, okay. So this was r, and if we want to mention this cos theta 1 in the form of these two things, we'll use this right angle triangle. So cos theta 1 base over hypotenuse, this is the hypotenuse, and we do not know the value of r1. So what is the base? The base is L by 2. And what is the value of hypotenuse? Basically, this square of this term, square of this term, दोनों sum कर लें, and the square root. So r square plus L by 2 square and under root. So you can see that we have mentioned the cos theta 1 in two the yeah, in terms of those things that were given to us, the L was given to us, the small r was given to us. So we'll put this uh, value back, L by 2 divided by r square plus L by 2 whole square. So this is cos theta 1. If we want to extrapolate the value of cos theta 2, we have to take a look at what the theta 2 actually is. Once again, we'll have to move back. Okay, so if we equate this theta 1 and this theta 2 together, we'll see that this is an equilateral triangle. We have placed this triangle at the origin, so it is an equilateral triangle. So theta 1 must be equals to 180 degrees minus theta 2. This is theta 2, and if we subtract theta 2 from 180 degrees, we'll get theta 1. So theta 1 is equals to 180 degrees minus theta 2. That means theta 1 is equals to 180 degrees minus theta 2. If we take cos on both sides, cos theta 1 is equals to cos 180 degree minus theta 2. This will be minus cos theta 2 cos theta 1. So it means that cos theta 2 is equals to minus cos theta 1. We have the value of cos theta 1. So cos theta 2 is equals to minus cos theta 1. That means it is minus L by 2 divided by r square plus L by 2 whole square under root. This is it. We'll just put this value back into this equation. H is equals to phi hat I over 4 pi r L over 2 divided by r square plus L over 2 whole square plus L over 2 once again r square plus L over 2 whole square. When we add these two things, this will be simplified into I L over r square plus L by 2. It will be transformed into this, and if we want to exclude this L over 2's 2, what we'll do is that we'll multiply and divide with 2. So if we multiply and divide with 2, this will be something like this. There is 1 over 4 pi r. Okay, so 1 over 4 pi r 2 il will bring this 2 into this square root. So this is 4r square plus L square. I hope you understand what's happening here. This 2 will be cancelled in this way. So phi hat IL over 2 pi r under root 4r square plus L square, and this is the value of H. Now if we want to calculate the value of B is equals to mu naught H. So we can put the value of mu naught here. This will be I hat mu naught IL over 2 pi r 4r square L square. This is the value of P for a current carrying conductor, and there is a special case. What's that special case? Is that if the length of the conductor is too large as compared to its radius. If the length is too large as compared to its radius, then this 4r square will lose its value, and there will be uh, only L that will remain. So I had, if I had is equals to mu naught I L divided by 2 pi r, and this will lose its importance because r is way less than small l. So this will be something like this L will cancel each other, and this is mu naught I over 2 pi r. So this is the most interesting and uh, fruitful outcome of what we have did today in this example. This is the equation that we have been studying from a long time. We have studied this equation in this course too. We have studied this equation in metric 2. We have studied this equation in FSC 2. This is basically the expression that gives us the value of B due to a current carrying conductor. And today what we did was that we tried to get a hold of the process. We try to comprehend the process, that how can we derive this equation, that how can we say that this equation is basically the equation of magnetic flux. Because up until now what we were doing is that we were just believing that the value of magnetic flux density in case of a current carrying straight conductor, this has to be this. But we never knew that how this equation came to be. So in today's example, what we did was we tried to comprehend, we tried to take a look at the process through which we calculated this expression. So there is another example. This example states how do we calculate the value of magnetic field for a pi-shaped loop. So what's a pi-shaped loop? I hope you know what a pi is. I'm not talking about the mathematical pi, where I'm talking about uh, pi shape. The pi shape is like the pizza's the shape of the pizza's piece. It is like this. This and this. This is a pi shaped loop. Okay, so he's saying that the direction of current is this and this is basically, he's saying that this is the observation point 2, and this is touching it, touching the pi's part 2. So what he's saying is that this is how the axes are placed. This is x-axis, and this is y-axis. This is point O, this is point A, this is point C, and this is the direction of current. Okay, so he's saying that give me the value for this pi shaped current carrying loop. Give me the value of H that is being generated at this point due to this pi shaped loop. So he's saying that for straight segments, which is, this is the example, for straight segments, which one are the straight segments? OA and OC. He's saying that for straight segments, the value of H is going to be 0. How can he say that? He's saying this because we know that the value of H has to be I over 4 pi, and then this is dl cross r hat divided by r square. So these two things have a major part, dl and r. He's saying that if this is the point at which we are observing the value of h, and this is the flow of current, so what will be the direction of r? This is the direction of r, and this is also the direction of dl in this case. So if these two things are parallel, it means that this cross product is 0, so H is 0. Same is the case with this thing. In this thing, the direction of DL and the direction of R, they are anti-parallel, and once again the value of H is going to be 0. So the value of H is going to be 0 for these two segments. But if we want to talk about this curved segment, we'll have to calculate the value of H for this thing. So if we take a small differential length dl, this will be the direction of dl according to the direction that has been given to us by the author. So this is the direction of dl. What will be the direction of r? This is the direction of r hat, and if we want to know the direction of h, we'll curl our fingers from dl towards r. So this, our thumb will be pointing towards, will be coming out of the screen. So if this is x, this is y, the direction of dh will be in z's direction. So we figured out what the direction of dl is going to be. It is in z's direction. And now we need to figure out what the value of dl cross r hat will be. So the value of dl cross r hat will be in z's direction. We figured this one out, and the remaining thing is dl. And what is dl? Dl, as it is a curved path, dl will be a d phi. What is a? A is basically the radius of this pi shaped thing. So a d phi. This is how we mention a differential length in case of a curved path. As you can remember, if you reflect back to the lecture that we took in vector analysis chapter. So a d phi, consequently h will be I over 4 pi. And what's the value of dl cross r hat? This is z hat a d phi. And what is the value of r square? This is basically the magnitude of r. The magnitude of r is a, so a square. This is 1 I over 4 pi a. A is basically constant, so it's coming out of d phi. So we don't know the value of d phi. He hasn't given us the value of phi, that what's the range for the mm, change in the value of phi. So we'll just replace this integral of d phi with a variable which is phi. So whatever the angle is, z hat over 4 pi a into phi. This is basically the value of h for the curved path of pi shaped conducting loop. So I think this is it for today. If there is something that's confusing you, you are welcome to ask all your questions in the interactive session. Thank you so much. Allah Hafiz.